All right, so we're going to talk about the second law of motion in this video. We finished our first law of motion, and when we were talking about the first law, we always talked about how when an object has balanced forces on it, or when it's at equilibrium, whether that's dynamic or static, that the net force is always zero. Well, now we're getting into something where the net force is not going to be zero. Newton's second law is about, well, it's based on a relationship between force and mass and how it relates to acceleration. We'll get into all that, but it's going to be a little more exciting than first law because there's actually stuff happening now. It's no longer just something sitting on a table doing nothing, or something traveling at constant velocity, constant speed, and straight line. Now it's going to be objects accelerating. Well, we already know that acceleration can be one of two different things. We know it can be a change in direction, or it can be a change in speed. We're always talking about in class that acceleration can be one of three things. It can be speeding up, it can be slowing down, it can be changing direction. And if any of those three things are happening, we say that the object is accelerating. We've talked about acceleration since the beginning of the course. We defined it, and we'll be defining it again mathematically here momentarily. Hey, speaking of that, here it is. So acceleration is delta v over t. You should remember delta v means VI minus, or VF minus VI, VF being the final velocity and VI being the initial velocity. So it's the change in the velocity over time. And its unit is meters per second squared. Again, this is all review. Should look familiar to you. There's really two variables that can affect acceleration. And the first is a net force. And when we think about this, this is common sense to most people. Maybe you knew this, but you never applied the math directly to it. That's what we'll be doing here in this unit. It says that acceleration is directly proportional to the net force. So the more net force you put on something, the more it's going to accelerate. The less net force you have on something, the less it's going to accelerate. So if I double the force, I double the acceleration. If I half the force, I half the acceleration. It is proportional, directly proportional. If I triple the force, I triple the acceleration. If I third the force, I third the acceleration. Very simple concept to understand, and it's common sense. If I have a shopping cart and I give it a small push, it's going to accelerate a little bit. If I have a big shopping cart, same mass as the first one, and I push it with a larger force, it's going to accelerate more. This is something that you don't think about when these things happen in everyday life, but we're applying it, as physics always does, we're applying it to real life situations. So let's take a look at the example here. It says solve for the net force. Well, I don't have any y components here, or any y vectors, so I'm just going to sum the forces along the x-axis. And we see that we have 25 newtons pointing to the right. We have 15 newtons of friction pointing to the left. And because they are in opposite directions, we are going to have them subtracted instead of summing them, adding them together. Well, that's really easy to see. The 10 newtons is going to be the net force, the overall net force acting on that object. So you may be on this side pushing it with 25 newtons of force, and the friction between the floor and the box might be 15. Well, you would be accelerating it to the right in a value of 10 newtons of force. So we say the net force and the acceleration are always in the same direction. Whichever way the net force is being applied, the acceleration is going to go the same way. That is not the same for velocity. We'll address that here momentarily. But let's say there's an applied force of 10 and the friction force is 50. Well, now we have an object slowing down because we have the applied force of 10 and 50 the other direction. Then we have a net force of negative 40 or 40 newtons to the left, and that's going to cause our object to eventually come to a stop. So in this case, the net force is to the left and the acceleration is also to the left, but the object itself is traveling to the right. It's coming to a stop. As you come to a stop sign in your car, as you get closer to the stop sign, you're traveling towards the stop sign, but your net force from your brakes and the car friction, the tire friction between the tires and the asphalt, is pointing opposite you, which means say the acceleration is pointing behind you. Even though you're moving toward the stop sign, acceleration is going away from you. All right, so take a look at this slide. We have an airplane, and it looks like along the y-axis, the forces balance out, 15,000 up, 15,000 down. But what about the x-axis? What do you see? I see the engine thrusting forward with 10,000 newtons, and I see the air friction or drag pushing against the jet with 6,000 newtons. So if we were going to sum the forces, along the x-axis, we would have 10,000 newtons to the right minus 6,000 newtons to the left. And of course, that's going to give us a net force of 4,000 newtons. The net force would be located along the x-axis and not along the y. Along the y-axis, it's balanced. Doesn't mean it's always going to be that way. You could have unbalanced forces along the x and the y. Then you'd have angled net force. But in this case, our upward force and our downward forces balance out. And it's just our x-axis forces that are unbalanced. So we would say this object's accelerating to the right, that the jet's accelerating to the right. Well, the second thing that affects the idea of acceleration is the idea of mass. And of course, mass, we know, is a measurement of inertia. The larger the mass something has, the greater inertia it's going to have. So an empty shopping cart and a heavy shopping cart, we know that the heavy shopping cart has more mass and therefore it has more inertia. The empty shopping cart, less mass, less inertia. So they are inversely related to acceleration. Mass is inversely proportional to acceleration. So if I double the mass, what's the inverse of doubling something? Halving it. I half the acceleration. If I half the mass, well, what's the inverse of halving something? Double it. You double the acceleration. And this is a real easy concept to understand. We can still use shopping carts to get this. If you push the same force on an empty shopping cart versus the same force on a heavy shopping cart, well, the heavy shopping cart is going to have more inertia. Therefore, you're not going to get the same acceleration. You're going to get less acceleration. If you have the same force on an empty shopping cart, the empty shopping cart has less mass. Well, less mass, inversely related, more acceleration. So here's the idea of second law, and sometimes the graphics think they know what they're doing and I have to switch it around. So yeah, this should be kind of a subscript. The net force is equal to the mass times acceleration. Normally though, it's easier to understand it when you write it in kind of a fraction form, where you can see that the numerator, which would be F net, you can see that it's directly proportional to acceleration. So if this went up, then the acceleration goes up. However, if you have the mass go up, in other words, that's the denominator going up, then the acceleration is going to be going down. Inverse relationship to mass, directly related to net force. And then, of course, just to review our idea of a Newton, we know that 1 Newton is equal to a kilogram meter per second squared. So it's the same thing that's written right there. So for me to cause something to accelerate, that's 1 kilogram by 1 meter per second squared, I would need to apply 1 Newton of force to that object. So this is just a review of the fact that kilogram meter per second squared is the same thing as a Newton. And if you're not sure where that's coming from, all you have to do is think of the second law. Mass unit is the kilogram. Acceleration unit is a meter per second squared. Well, when you multiply those together, nothing cancels out, and you're left with a kilogram meter per second squared, also known as a Newton. And as I was saying earlier, this is the typical way, or the easier way to understand what the second law is talking about, where you have net force on the top and then mass on the bottom. Now, if you think about it, this idea of weight is just a modification of the second law of motion. We know that the net force is equal to the mass times the acceleration. Well, one type of acceleration is gravitational acceleration, g. So when we write this formula out for weight, we see that it basically is the second law of motion, where g is always 9.81 meters per second squared. So when we're trying to calculate our weight from a mass, and we simply multiply by 9.81, believe it or not, we're just using the second law of motion for that. One thing that you need to remember that's very common, it comes up quite a bit in this course when we're talking about mechanics, is this idea of acceleration, net force, and velocity. And here's the rule. When you have a net force in whatever direction that net force is, the acceleration is always, capital A there, always going to be going in the same direction as the net force. Acceleration and net force always point in the same direction. The velocity, however, sometimes can point opposite. I'll give you an example. If you are driving a car and you are coming to a stop sign, you are going to eventually come to a complete stop. Your velocity is towards the stop sign. But because you are slowing down, your acceleration is in the opposite direction of the velocity, and therefore your net force is in the opposite direction of velocity. If you are at that stop sign and you start to speed up after you come to a complete stop, your velocity is still forward, and now your net force is forward, and therefore your acceleration is forward. So it is possible for all three to point the same way: acceleration, velocity, and net force. But velocity doesn't always have to point in the same direction as net force and acceleration. Net force and acceleration, however, always point the same direction. All right, so let's take a look at some examples here to state whether the net force and acceleration is in the same direction as the object's velocity. So we have a first one: a dragster goes from 0 to 100 kilometers per hour in 2.3 seconds. I think you can tell from the way that it's written that it is speeding up. It's getting faster. So this will just be like the second part of the example previously. So the velocity and acceleration are the same direction. So it's the same direction here for that one. A motorcycle slows from 80 miles per hour to 0 miles per hour in 5.2 seconds. So now this could be like our motorcycle or our stop sign example, where we're coming to a stop sign and we're slowing down, where velocity is still going towards the stop sign, but the acceleration and net force are going the opposite way. So this would be opposite. A driver in a pickup driving in reverse slams on the brakes and comes to a stop. A lot of students want to put same here because they think the direction that the pickup's driving, or the fact that it's driving in reverse, makes a difference. It does not make a difference. It's still the same idea as the motorcycle one just before it. So this is still going to be opposite. The fact that the truck's driving backwards doesn't make a difference. After being kicked, a hacky sack is traveling vertically upward. Well, what's happening as the hacky sack is traveling upward? What is it doing? Is it speeding up in velocity or is it slowing down? Well, as the hacky sack heads up into the air, it is slowing down. It's getting less and less, which means that even though the velocity is up into the air, the acceleration and net force are down. So this would be opposite as well. And then the last one, a hacky sack is falling towards Earth. Well, now it's getting faster. So the net force is down, the acceleration is down, and the velocity is down. So this one would be the same. All right. A 30-kilogram scooter undergoes an acceleration of 2.3 meters per second squared. What is the magnitude of the net force experienced by the scooter? Well, this is as easy as you might think, but let's go ahead and write out our given values. We have a mass given of 30 kilograms. We have an acceleration given of 2.3 meters per second squared. And we're asked to find net force. Well, we know net force is equal to the mass times the acceleration. And we're given the mass right there, 30 kilograms. And we're given the acceleration, 2.3 meters per second squared. So it's just a little plug and chug problem. And 69 newtons is your answer for that first one on this slide. Pretty straightforward, I think. A Boeing 777 has two turbofan engines that each produce 444,800 newtons of force, of thrust. The 777 has a mass of 230,000 kilograms. What is the acceleration of the airplane at full thrust? And we're supposed to ignore air resistance. So they give us the mass at 230,000 kilograms. They give us the thrust. Now thrust, what is that an example of? Well, look at the unit. The unit is in newtons. So what does that tell you it's a unit of? It's a unit of force. So thrust is a type of force. So the force is 444,800 newtons. But it's two different engines. So we need to change those two to 888,600 newtons. Now we have our overall force, and they want us to find the acceleration. Well, we know acceleration is the force divided by the mass. We know that because if we take F equals ma, and we rearrange it to solve for acceleration, we know that's F over m. So I'm going to take my F, 889,600, divided by 230,000. And that's kilograms. When we divide 888,600 divided by, or 889,600 divided by 230,000, we get 3.9 meters per second squared. So that would be our acceleration for the Boeing 777. Just to reference this, how do I get meters per second squared from a Newton over a kilogram? Well, remember, a Newton is a kilogram meter per second squared over a kilogram. So kilograms end up canceling, and what are you left with? You're left with meters per second squared. The last one on this slide, a 68 kilogram person, so that's the mass, steps on a bathroom scale. What does the scale read in newtons? So they're asking us for weight, and we know that weight is m times g. Well, we know m already, and of course we know g as well. We've been using g since we started the school year. And that means that we simply take our formula for weight equals m times g, and we plug in 68 kilograms, divide or multiply that by 9.81 meters per second squared. And when we do that, we end up with 667 newtons for our weight. So pretty straightforward for that. All right, so we have a Boeing 767 touchdown at 63 meters per second. So as it's landing, it hits the ground going 63 meters per second and comes to a rest 27 seconds later. So hopefully you can read into that the final velocity here is 0. If the mass of the 767 is 74,000 kilograms, what is the net force on the aircraft? All right, so we have a mass of 74,000 kilograms, and we have a VF of 0. We have an initial velocity of 63 meters per second, and we're asked to find the net force. Well, we know net force. We know that equals the mass times the acceleration. And we have a mass given, but we don't have an acceleration given. But I do know that acceleration is equal to VF minus VI over t. That's something that we learned way, way back at the beginning of the school year. So I could actually substitute in my acceleration formula here. Mass times VF minus VI over t. And that would give you my net force. So let's take a look. The mass is 74,000. The acceleration would be 0 for VF minus 63 for VI over my time. My time was 27 seconds. Oh, I forgot to put that in the given values, times 27 seconds. So I end up with 74,000 kilograms. And then negative 63 divided by 27, that's negative 2.3 meters per second squared. And then we simply multiply the 74,000 times the negative 2.3 meters per second squared, and we end up with 170,200 newtons, or 1.7 times 10 to the 5th newtons. And we see that the acceleration is negative, which should make sense because the object's slowing down. It has a positive velocity, and it's going to have a negative acceleration in this case. So there's our answer. All right, it says find the magnitude and direction of the net force. It says a football player is tackled by two defenders and experiences two simultaneous forces as shown in the diagram below. Ignore any other forces. All right, so we have a force of 250 newtons being applied one direction. We have a force of 120 newtons being applied in another direction to the right. And we're supposed to determine the overall position of the net force. Well, if we did our parallelogram method, what we're trying to do is find that vector right there, and we're trying to find that angle. You could also draw it like this, a little different than you see in the picture on the left there. 250 this way, and then 120 to the right. And it would end up being the same exact vector. It really doesn't matter which one of these angles you decide to find, as long as you are specific in how you describe them. So how are we going to determine the hypotenuse of this right triangle? Well, I hope that by now it's become second nature to you to know that's going to be the Pythagorean theorem. So we know a squared plus b squared equals c squared, where c is our hypotenuse. So c is equal to the square root of a squared plus b squared. And does it matter whether we call the 250a or the 120a? It doesn't make a difference. So I'm just going to plug in my numbers here. A squared is 250, and b is going to be 120. So we end up with the square root of 62500 plus 14,400. And we end up with 277.3 newtons, and that's the magnitude of the force. So the magnitude of the force, but it also says find the direction. So now we have to decide on the direction. And if we were going to find this angle here, the opposite side would be 120, the adjacent side would be 250. And I would want to determine which trig function to use. Well, I know the opposite and I know the adjacent. So that, to me, the easy would be tangent. I know tangent of the angle is equal to the opposite side over the adjacent side. TOA, right? SOHCAHTOA. And if I'm trying to find just the angle, then I need to do the inverse tangent of both sides. And the inverse tangent of the opposite side is 120. The adjacent side is 250. So what is the inverse tangent of 120 over 250? Well, that would be 25.6 degrees. And that would be to the right of the positive y-axis. That would be one way to find it. You could also subtract that from 90 to get this angle here. And that would end up being 64 degrees, 90 minus 25.6, above the positive x-axis. All right, same directions here. Find the magnitude and direction of the net force. It says a Formula One race car is hit simultaneously by two other cars. Ooh, sounds horrible. As shown in the diagram below, ignore any other forces. So we have a force moving this way that is 7,900 newtons. We also have a force hitting this car this direction. That's 3,500 newtons. And if we were going to look at it in terms of parallelogram method, we would be trying to find that hypotenuse and maybe this angle. We could also draw it 7,900 newtons this way, and then 3,500 newtons this way. And it would be the same hypotenuse that we were trying to find, that angle there. And of course, we could also find that angle if we wanted to, either way. And this is setting up to be just like our previous problem where we just have a right triangle to figure out. And we go ahead and we draw out our formula. A squared plus b squared equals c squared. And we know we're trying to find c. And we know c would be the square root of a squared plus b squared. Doesn't matter which one we label, a or b. So 7,900, I'm going to label that as a. 7,900 squared plus 3,500 squared gives us 62,410,000 plus 12,250,000. And we end up with C equaling 8,640.6 newtons. And that's the magnitude of the force. So there's the magnitude of the force, 8,640.6 newtons. And then to find the direction, we have to find that as well. Well, let's see, we know the opposite is 3,500. We know the adjacent is 7,900. So I'm going to use tangent again. Tangent of theta equals the opposite over the adjacent. Inverse tangent on both sides of opposite over adjacent. Now I just have to plug in my numbers. The inverse tan opposite side would be 3,500. Adjacent side would be 7,900. And the inverse tangent of 3,500 over 7,900. By the way, make sure you're in degree mode here. If you're in radians, you need to switch it to degrees. Would be 23.9 degrees below the negative x-axis. This angle here. And then if we wanted to write it in a different way, we could just subtract that from 90. 90 minus 23.9 is 66.1 degree, and that would be to the left of the negative y-axis. So that would be an appropriate direction as well. Either one of these directions will be fine. The magnitude, there's only one answer for that. All right, same directions as the previous two. Find the magnitude and direction of the net force. On this one, though, it doesn't look like it's a right triangle problem, but if you sum the forces, it will be. We have, along the y-axis, we have 10,600 newtons going up, and we have 9,250 going down. Well, when we have vectors pointing opposite ways, we would subtract the two values because they're going opposite directions, and we end up with the sum of the forces being 13 90 newtons up for the y-axis. And for the sum of the forces along the x-axis, we have 40,000 to the right minus 35,000 to the left. And we subtract them because they're pointing opposite directions. And 40,000 minus 35,000 gives us the sum of the forces in the x direction as 5,000 newtons to the right. Doesn't say east, so we can't put east, just say to the right. And now we have two legs of a right triangle. We have the airplane force 1350 going up, and we have the x direction 5,000 newtons to the right. So that they want us to find the hypotenuse. They want us to find that. You could have drawn it parallelogram method if you wanted. Draw it like that for the 1350, and then that for the 5,000. And then we would have this hypotenuse to find. But again, that would be the exact same hypotenuse that you're looking for. And then theta would be the angle that we're trying to find. So again, what we're doing here is we're just doing a little Pythagorean theorem, because that's all this is. This is a right triangle. So a squared plus b squared equals c squared. And c would be the square root of a squared. Doesn't matter which one I call a squared. I'm just going to pick 5,000 plus b squared. I'm going to do 1350 for my b squared, my b. And then we end up with 25 million for 5,000 squared. And we end up with 1,822,500 for the 1350 squared. And we end up with an overall magnitude of net force of 5,179 newtons. Magnitude of force. So that would be the first answer. And then we have to find the direction. So again, we're just trying to find theta. And we know the opposite's 5,000. We know the adjacent's 1350. So just like we did on our previous examples, tan of the angle equals adjacent over hypotenuse, over sorry about that. Tangent of theta equals the opposite over the adjacent. And to get the angle, we know we're going to have the inverse tangent of the opposite side. What would the opposite side be of theta? Theta would be 5,000, or the opposite side would be 5,000 over the adjacent side, 1350. And when we do the inverse tangent of 5,000 over 1350, we end up with 74.9 degrees to the right of the positive y-axis. So that would be our answer for the angle, but you could also have the angle, subtract 74.9 from 90. That means you're finding this angle here, and that would be 90 minus 74.9 is 15.1 degrees above the positive x-axis. So this would be an acceptable degree and the one down here would be acceptable degree. But the force, 5,179 newtons. That's the only answer for. All right, find the magnitude and the net force and the acceleration of the object. Well, when you see this, find the acceleration of the object. Usually when we're in second law and you see find the acceleration, you have to understand that it can't be zero in this case. So there's going to be unbalanced forces acting on this object. Well, what object do we have here? This is a 50 Newton box. So I'm going to draw my FW vector. And that's 50 newtons. It's pushed horizontally to the right with 40 newtons. So this would be FA of 40 newtons. The coefficient of kinetic friction between the object and the surface is 0.65. So that's going to come in handy later on. And there are some other things that I can fill in. I know this is going to be normal force. Remember, this is normal force with just the N. If it said F net, that's net force. Which way will friction be? Well, if the object's being pushed to the right, friction's always opposite the motion, then we know the friction force is going to be to the left. So that is the force of friction kinetic. All right, so our free body diagram looks good. And now we have to set out to find the net force. Well, first off, I need to decide on how I find my normal force, because that's going to help me find my friction force later. If you know that the friction force, and this is just off of your formula sheet, is equal to mu k times the normal force, and you already know mu k, if you could find the normal force, that would allow you to solve for the friction force. And then we could tell which way the object's accelerating. So how am I going to find the normal force? Well, it's being pushed horizontally, so it's not moving up into the air, it's not moving down in the ground. So it's just even, it's balanced along the y-axis. So the sum of the forces along the y, I know it's going to be my weight minus my normal, and those are going to be set equal to 0 because along the y-axis, forces are balanced. Well, we know FW, we know it's 50. And if we know FW, we know normal. Normal force is 50 newtons. So if I know the normal force is 50 newtons, I'm going to use that along with my mu k to help me find my friction force. So friction force equals mu k times normal. And mu k is 0.65, and normal force is 50 newtons. So the friction force is equal to 32.5 newtons. Okay, so let's go back to our picture here. 32.5 newtons of friction force. How much is being pushed to the right? 40. Which one of these is greater, 40 or 32.5? Well, the 40 is greater, which means this box is accelerating to the right. Along what axis? Along the x-axis. So to help me solve for the net force and ultimately the acceleration, I'm going to sum the net force. Now, some of you may prefer to put an x here because it's along the x-axis, but you really don't have to do that. You know it's along the x-axis. Along the y-axis, it was balanced. So along the x-axis, it's unbalanced. And what two forces do I have going along? I know FA and I know friction. They're both going along the x-axis. Now, what is all that going to be equal to? Well, we know, again, from the second law, that the net force is equal to the mass times the acceleration. Well, here's the net force. And what is that equal to? It's equal to the acceleration, ma. So FA is 40 newtons. friction force, I solved for that already, it's 32.5 newtons. M, I could solve for that if I wanted to. Let's see. What is the formula to solve for the mass of something if you know the weight? Well, think about it. You know the weight. If you know the weight is mg, and you want to know the mass, wouldn't you just divide weight divided by g? And the weight's 50 newtons, and g is 9.81 meters per second squared. So what's the mass of this object? Well, the mass of the object is 5.1 kilograms. So I'm going to use that over here. 5.1 kilograms times my unknown. My unknown is acceleration. Now the net force is going to be 40 minus 32.5, and that's going to be 7.5. So there's my answer for net force, and that's equal to 5 kilograms times A. We're trying to find A, so A would be the net force divided by the mass. The net force is 7.5 newtons. The mass is 5.1 kilograms. And the acceleration is 1.47 meters per second squared to the right. So there's your acceleration value. Here's your net force. Here's your acceleration. All right, find the net force and the acceleration. So let's go ahead and complete our free body diagram here. We have an 18.5 kilogram box pushed horizontally to the left with 220 newtons. So it's being pushed to the left. So that would be our FA, 220 newtons. We know we're going to have a weight vector. That's FW, and it would be mg, right? So let's go ahead and we can calculate that real fast, mg. And we know that that's going to be 18.5 kilograms times 9.81 meters per second squared. So we know that our FW is 181.5 newtons. We know our normal force is going to be going up this way. And which way will friction go? Well, it's going to go opposite the direction of the object, in this case to the right. And that's going to be kinetic friction. And they give us the mu k value as 0.55. So what will be our next step? Well, we really need that friction, because if we know the friction, now because it's moving horizontally, we know it's accelerating along the x-axis, which means that the unbalanced forces are along the x-axis. So if I could find the friction force, then I could figure out what the net force is, because the net force would be the difference between my FA and my friction vector. So how are we going to find friction force? Well, we know friction force is equal to mu k times normal force. And mu k is 0.55. Normal force, don't know that. Or do I? Well, I know that if I sum the forces along the y-axis where the normal force is located, I know I have Fw, and I know I have Fn. And I know because it's not being pushed up into the air or pushed down into the ground, I know that it's balanced along the y-axis. And if the weight is 181.5 newtons, then the normal force is 181.5 newtons. So I'm going to plug that in right here, 181.5 newtons. And that means my friction force is equal to 99.8 newtons. All right, so we have what we need. We need that friction force, and now we have it. So which axis is the unbalanced force on? It's on the x-axis. Again, it's on the x-axis. And what two vectors do I have? I have Fa on the x-axis, and I have friction. Why am I subtracting them? Because they're going opposite ways. And what will they end up equaling? Well, usually we'd set them to equal to 0 if this was first law, but now it's second law. So we set it equal to Ma. And Fa is 220. Friction force is 99.8. M is 18.5 kilograms. And A, we don't know. So what's 220 minus 99.8? Well, that's a net force of 120.2 newtons. So there's our net force. That's the first part of our answer. And what's that equal to? That's equal to the mass times the acceleration. So if I'm trying to find the acceleration, I simply divide both sides by 18.5. And when I do that, I end up with 6.68 meters per second squared. And that would be to the left. So there's your acceleration. There's your net force. We finished that sample problem. All right, so this problem says find the net force and acceleration. Okay, 45.5 kilogram sled is pulled with 200 newtons of force by a rope at a 30-degree angle to the ground and accelerates. The mu k between the sled and the ground is 0.39. All right, so we can go ahead and include our free body diagram over the picture here. So we know we're going to have this red vector here. Actually, it'd probably be better if we draw it off to the side. Let's do it this way. So here's our sled. And here's our applied force. And that applied force is 200 newtons. We know that the weight is going to be Fw, and we know that Fw equals mg, and mg would be 45.5 kilograms times 9.81 meters per second squared. So we know Fw is 446.4 newtons. Our normal force is going to go this way. And our friction force, well, we're trying to move the slide to the right, so our friction is going to go to the left. And it's going to be kinetic because it's in motion. And the last thing we would need to draw is our components for our Fa vector. And remember, we have to do that because it's at an angle. And any angle is going to have, any angled vector is going to have components. So there's Fax, and there's Phi. So here's Phi, and here's Fax. And we also have a 30-degree angle. Okay, so what else are we given? Well, we're given mu k is 0.39. And that's everything that's given, and they want us to find the net force. Well, we know it's moving horizontally. He's not lifting it up into the air. It's just accelerating to the right, which means our Fax is going to be greater than our friction force because they're pointing in opposite directions. But what about along the y-axis? It's not being lifted up. It's not being pushed down into the ground. So it's simply balanced along the y-axis. But along the x-axis, it's not. All right, so let's think about it. If I wanted to find the friction force, and I know friction force is equal to mu k times Fn, is there a way for me to find Fn by summing my forces and then plugging that into my formula here to find friction? There certainly is. So let's do that. Let's sum our forces along the y-axis. So if we sum the forces, what do we have along the y-axis? We have Fw, we have Fn, and we have Fe. And Fw points the opposite of Fn and Fay. So Fw minus, and what two things will I sum because they're both pointing up? Well, it would be Fn and Fay. And because it's not being accelerated up into the air and it's not being pushed down into the ground, those forces are going to sum to 0. So Fw, well, I know Fw, I know it's 446.4. Fn, I don't know. That's what I'm after. Fay, well, is Fy the opposite side to our right triangle up here in the diagram? And we know this is 200. So this is the angle 30. So the Fay is going to be 200 sine 30. Fay is 200 sine 30. And so we work it out, 446.4 minus 200 sine 30. 200 sine 30 is 100. And that means that Fn is 346.4. So now we have enough information, we can come over here and we can solve for friction. And we know friction is the mu k value, 0.39, times the Fn, 346.4 newtons. And that means our friction force is 135 newtons. 135 newtons. So there's our friction force. And we know that that friction force, the 135.0 now, we know it's pointing to the left. We know it's accelerating to the right. So we know Fax, it's got to be greater than 135. Because if it wasn't, if it was the same, it wouldn't be accelerating. So how do we figure out what Fax is? Well, Fax is along the x-axis. Friction is along the x-axis. So I'm going to sum my forces along the x-axis. I have Fax minus friction. Now again, friction is already something that we solve for. And what would Fax be? Well, Fax is located along the adjacent side of the 30-degree angle, and the hypotenuse is 200. So Fax is going to be 200 cosine, right? Cosine is adjacent over hypotenuse, and rearrange. 200 cosine 30 minus the friction force, which is 135. And I made a bit of a mistake here. Let's go back and double check this right there. That should actually be written as MA because we know that it can't equal 0 because the forces are not balanced. So that should be MA. Because this right here, what I'm solving for, this is the net force. So a better way of writing it, let's go ahead and fix that. Better way of writing this would be F, the sum of the net force. And this would be along the x-axis. So what is 200 cosine 30? 200 cosine 30 is 173.2 minus the 135 that I already had. And what does that give us? that gives us 38.2 newtons. So that right there is the net force. Well, what does that equal? That equals MA. Well, what's M? M's way, way up here. M was 45.5 times our unknown, acceleration. And how am I going to solve for the acceleration? Well, it's going to be 38.2 newtons divided by 45.5 kilograms. And I end up with acceleration of 0.84 meters per second squared. And there's your answer to that problem. So the last problem on our second law notes says find the magnitude of the net force and the acceleration of the object. An Olympic skier with a mass of 65.5 kilograms is moving down a 23-degree slope. The coefficient of friction between the skis and the snow is 0.19. All right, so I think for this one, we probably can get away with putting the free body diagram right over top of our picture. Let's see if we can get that done. So there's our FW. And we know FW equals mg. And m in this case is 65.5 kilograms. And the gravity is 9.81 meters per second squared. So FW for this one is 642.6 newtons. So that's our FW. We know our normal force is always going to be perpendicular to the surface, so normal force goes right there. Let's see, the skier is moving down the hill, so which way should friction point? Friction should point up the hill. And it's kinetic friction. And now I'm going to make my components. And my components are going to, remember you always use normal force as your guide. And that's going to go straight down away from normal force. And then it's going to make a right angle here. And that right angle is going to form our other component. And this is FWY. And this one is FWX. And we said it was a 30-degree angle earlier, or excuse me, 23-degree angle. So that's 23 degrees right there, which means that our angle right here is 23 degrees right there. All right. So what's pushing the skier down the hill? Well, it looks to me like there's only two things that are pointing along the x-axis, which would be the incline. And that's FWX and friction force. And it says that they are accelerating down the hill. And if they're accelerating down the hill, that means our FWX is going to be greater than our friction force. But once again, like the previous problems, we can't find the friction force to help us solve for net force without first finding normal. Because remember, we know mu that's given to us, mu k, is 0.19. And we know that the friction force equals mu k times the normal force. But we don't have the normal force. Where is the normal force located? It's along the y-axis. Does it say the skier is being pushed up into the air or pushed down into the ground? It does not, which means that we have a balanced set of forces along the y-axis. So I can figure out what Fn is if I sum my forces along the y-axis. And I only have two vectors along the y. I have normal and I have Fwy. And those will balance out to 0 because, again, along the y-axis we don't have any unbalanced forces. Well, normal, I'm just going to drag that along because I don't know it yet. Fwy, is Fwy adjacent to the 23 or is it opposite? Fwy is adjacent to the 23. And what would the hypotenuse be? Well, it would be 642.6. So instead of writing FWY, I can write 642.6 hypotenuse times, and it's adjacent, we said, the cosine of 23. So 642.6 cosine of 23. Well, we can go straight to the answer for normal force here. Plug that in, and we end up with 591.5 newtons for our normal force. Now I can take that normal force and I can use it to plug in to find friction force. So let's do that. The mu k was given, it was 0.19. Normal force is 591.5 newtons. So the friction force is going to equal 0.19 times 591.5. And that gives us 112.4 newtons. So friction is pushing against the skier with 112.4 newtons. But the skier is accelerating. And we know Fwx is going to have to be greater than friction force, because that's the only way that you could accelerate is if the down the hill force is greater than the up the hill force. So what I'm going to do is I'm going to sum my forces for the net force. And there are, in other words, along the x-axis, because that's where the acceleration is taking place. So I have Fwx, and I have friction. Now they're going opposite ways, so I'm going to subtract them. And what will the net force equal to? Well, again, what is the second law of motion? F net equals ma. So I'm going to put ma over here. Fwx, is it opposite the 23? If you go back and look at the picture, it is opposite, so we're going to use sine. What's the hypotenuse? Hypotenuse is 642, so 642.6 newtons. Sine, because it's opposite, 23, minus my friction force, which I already know is 112.4, equals the mass. The mass is given, right? The mass is given right there, 65.5 kilograms, times my acceleration, which is what I'm after. So what's 642.6 newtons? Sine 23, well, that's 251.1 minus 112.4. That gives me a net force of 138.7 newtons. So there's the first half of my answer, and that equals 65.5 kilograms times the acceleration. So how am I going to find the acceleration? I'm simply going to take my net force, which is 138.7, and I'm going to divide that by the mass, 65.5 kilograms. And we end up with 2.12 meters per second squared, and that is my acceleration for the skier.